CLI and a cross-platform IDE for C and C++. Download now.
Thank you for joining me for my talk today, Purging Undefined Behavior and Intel Assumptions and Legacy Codebases. Hope you're having a good afternoon, evening, morning, wherever you are in the world today. As we go along, I'm going to try my best to monitor the Q&A in Zoom and in Discord. And so feel free to ask questions in either places as we go along. And of course, we also have the Q&A afterwards. I'm Roth Michaels. I'm a principal software engineer at Native Instruments. And before we go into this talk, just want to mention that thank my former colleague, Russell McClellan, who worked with me on co-writing an earlier version of this talk that we gave together a number of years ago. And just to give you a little bit more about my background, I work at Native Instruments, which is a group of audio companies that merged together about 4 or 5 years ago. Native Instruments, Isotope, and Plug-in Alliance Brainworks. Most of these stories are coming from the Isotope era, from before the merger, just as some context. And we make audio software, both hardware and software for digital audio. So that's both for mixing and mastering records, producing beats, DJing, post-production for film and television. And one of the particular challenges is often we're running as a plugin or a DLL in some other process and host application that we did not write and don't have control over. And so it's not only UB that we have to worry about in our plugins, but sometimes there's also kind of strange stuff that has come along the way when there's UB going on that is a kind of a team effort between different plugins screwing around in somebody else's C++ process. And before we get into the details of the talk, I just wanted to mention something that I often am doing at the beginning of my talks. This was something I was inspired to do at a panel I saw hosted by Include C++ a number of years ago, which is to encourage all of you that are listening at the moment to consider giving a talk someday if you haven't. Those of us that are giving talks at conferences aren't some magical experts. We're just some people that have learned something interesting and want to share it with you. And I'm sure all of you have had some interesting story or experience at, your either work or hobby programming that would be interesting to share. And the more different voices we have sharing at conference community, the better. And you can start off with applying to give talks or even just a lightning talk at some conference. If you're concerned about how to prepare and stuff, the Include C++ Discord is a good place to go. They have a channel, I think, in there for discussing conference talk proposals and getting feedback. I think I might have done that once, but I'm usually such a procrastinator. I don't have a whole lot of time to ask people for feedback. But anyway, let's begin. Before we get talking about too much details about undefined behavior, I just want to ask if anyone, I don't know if anyone's in the Discord in the moment, because I know this is normally just a little interactive thing I do live, but as anyone sees something that is wrong with this function, other than being a really, really bad and not real random number generator? Well, so we haven't had anyone chime in. I'll just kind of tell you that this is a little joke I told at the start of this, but to make a point that yeah, at the same year I gave this talk, originally I was also giving a talk about good approaches to random number generators. And the joke here was a lot of people are saying, oh, you're returning an uninitialized variable. That's the problem. But the real problem with this function is that it's missing a semicolon, and this wouldn't compile. And my point about this is that I remember the first time that I ever got a warning, maybe like 2012, when compilers started telling you, hey, I think you have a semicolon missing here, versus some really cryptic message about whatever it got confused about as it was trying to compile past that semicolon. And also, what people might be pointing out initially for this interactive portion is that this would be undefined behavior returning an uninitialized variable. In C++ 26, it's no longer undefined. It's actually something new called erroneous behavior, which I'll get into in a moment. I'm just looking at the question in the chat. Michael, I'm not sure I fully understand your question, but we'll come back to that at the end, and hopefully maybe we can clarify in the gather town. But my point about the semicolon is our tools are getting better all the time. And so pointing out that semicolon is one thing, but there's a lot of other great tools that we'll get into that help us deal with undefined behavior. And C++ is really, really hard for humans or AIs to write correctly. So using as much tooling as we can to make sure that our C++ is actually legitimate, good C++ is something highly encouraged. And like the later part of this talk, we'll get into tooling. So what's going to happen, just as an example, thinking about like what's the kind of concern about undefined behavior? This function here, what might happen when you do this? Some people might say, oh, it's going to crash because you're doing undefined behavior. Or some people might say that it's, like we said, going to return a random number. Or, as some people like to colloquially say, it could summon nasal demons. And, well, no, it's unlikely that that's something like that, that you're going to sneeze because of undefined behavior. We'll see in some other examples about how crazy stuff can happen with the optimizer that theoretically maybe something happens and like some dust comes out of your computer and makes you sneeze. But this is kind of hyperbole with the point of scaring people about undefined behavior, which I think has some value. This fear that anything can happen, because some people don't take it seriously and don't realize how ununderstandable invoking undefined behavior can make your program be. But I do recommend this talk by Chandler Carruth that talks about why the nasal demon argument, maybe that level of hyperbole isn't helping, and kind of talks about kind of the kind of real world issues with undefined behavior. So again, we'll go back to this function, and often people might say, oh, this is going to return a random value, or the standard might say the value of this is indeterminate, even though it's undefined behavior. And what we'll see is if we compile this with Clang without optimizations, the key part of what this function does is it's going to read some value from the point in the stack where that X is, even though there's nothing there. And so, yeah, this is the kind of garbage memory or random value you might think will happen. But the point about undefined behavior is the compiler is allowed to assume that that is never going to happen. So if the only thing in this function is invoking undefined behavior by returning X, the compiler is going to think, oh, well, that's impossible. That's never going to happen in my world because that's impossible in C++. So instead, with an optimization O3 on, Clang will compile this as an empty function that just returns because it really could do anything. But obviously, if all this function does is invoke undefined behavior, the compiler can assume it will never be called in a real program, and so can just optimize the whole thing away. And so that's really why undefined behavior does such confusing or scaring things, is when the optimizer assumes something's never going to happen, and then it does, that you can have surprising results. Also, another kind of, I don't know if anyone is active in the Discord right now, but usually if I do this live, I would ask for a raise of hands of who's written undefined behavior on purpose. And, there's even things I'm saying like, oh, yeah, I've done it. And I can tell you, I've done it myself, and then looked at the assembly output, the code gen, and thought, oh, yeah, this does what I think it does. And it happens to work. And that particular example, everything seemed to go fine. But these days, my attitude is there is no writing undefined behavior on purpose. It's really something that should be always avoided. And kind of related to this, I really like this XCD comic. There's lots of things that this could be referring to, but I think attitudes around being nonchalant about undefined behavior fit this comic quite well. So I'll kind of give you all a moment to take a look at this if you've not seen this one before. Yeah, so I don't think it's that like our industry is actually bad at what we do. I think we have a lot of talented engineers in our industry that try really hard, but uh, you know, um, C++ is also a really hard thing to deal with. This is something kind of internally on our team. We used to joke about we got some feedback on a forum about details don't really matter, but a small feature we implemented that a decade prior might have helped out users, but due to changes in the host programs that we run in, it became an annoyance. And we'd actually already taken the feature out, but not shipped it yet. And we found this guy on one of the audio software forums, Dr. Driller, complaining about why don't they just fix this or take this out? And that those guys are clearly not serious programmers. And we took that as a badge of honor. No, we aren't very serious. We actually have a lot of fun with what we do. But we do take the craft very seriously. But as I said, C++ is hard. I don't know where this quote came from, but C++ is enough rope to shoot yourself in the foot. And I think that's true. And it's not just the issue with undefined behavior that, oh, we made some like bad mistake at the time. But I like this quote from Titus Winters that software engineering is programming over time. And some of the real world examples we'll get into later, the issue wasn't that like somebody didn't know what they were doing a while and wrote some buggy code on its own, but something that was thought to be safe maybe when it was written 10 years ago, when reused in a different way, invoked undefined behavior that maybe was never invoked before. So for the kind of meat of the talk, we're going to kind of talk about 4 different things. An overview of what undefined behavior is, some examples of interesting bugs that I've seen that were caused by undefined behavior, and then how we made big changes at Isotope to both change the culture to actually have an attitude of fighting undefined behavior and really caring about these things, and also tooling changes we made to help in this process of making sure we're not adding new undefined behavior to our code base. So what is undefined behavior? If you think about a C++ program, there's a kind of a number of different kind of states that something can be as far as expressions and behaviors of the program. So an expression can be well formed, and that's a normal thing that compiles. But then we have a couple other interesting. So you have ill-formed expressions or code in C++, and that's something that's not going to compile, and you'll get a compiler error. We also have things that are ill-formed, no diagnostic required, but this still means it's not a legitimate C++ program. The point of this is that it would be a compiler error, but it's potentially too hard to actually create an error. An example of this is an ODR violation, where if you have 2 definitions of a function with the same names and input arguments, so the same name mangling, but they actually have 2 different implementations. Sometimes you will get a linker warning for this, but that's not something that's required to give an diagnostic. And so this is kind of a scary concept that, if you do something that's ill-formed, no diagnostic required, it compiles, but it's technically not a real C++ program. It's kind of something else. And as far as the runtime behavior of your programs, you have defined behavior, where that's the deterministic behavior, like kind of the standard libraries, the standard document says this is what happens. You kind of think about this as guaranteed behavior. We'll get into definition of all this stuff. We have implementation defined behavior as well, unspecified behavior, undefined behavior, which is our main topic, and then a new one, erroneous behavior. Regarding the ill-formed, no diagnostic required, also a scary thing, not necessarily like undefined behavior, but I really like this talk from Titus Winters, What is C++, which is the first time I came across that concept. So what are these different kinds of behavior? You can think about it, and what's something important to keep in mind is the C++ standard doesn't really talk about how computers work. It's a description of an abstract computational machine. So, for example, things like including header files. Well, there's no such thing as a file necessarily in the standard in that case. And so this abstract machine that the standard describes has different behaviors, some of which are deterministic and some are non-deterministic. And so this is kind of, why you might see stuff that's guaranteed or platform-specific behavior. So there's the defined behavior. This is the deterministic part of the abstract machine. And then you can have implementation defined behavior. And so this is non-deterministic behavior, like what's the size of an int? What's the size of a long? Is car signed? And platforms can choose this. but they must document it. And then there's unspecified behavior, which is again, non-deterministic. When I say that, I mean it's not going to behave the same across all platforms and compilers. There might be suggested by the standard, but you don't have to document it. It just must be one of a set of valid results, like order evaluation or are all string literals the same thing. And then the main point of this talk is undefined behavior. This is something that standard makes no guarantees about, and compilers can assume this never happens in your program. And since it can assume it never happens, it can optimize under those assumptions, and really anything is allowed as a result under the standard when this happens. This is why people say, oh, undefined behavior could format your hard drive. Well, no, you're not going to have a malicious compiler that's going to format your hard drive on purpose if you dereference some int. But we'll see some examples where really surprising things can happen. And if delete your hard drive was in that function, it could happen. And then there's this new thing that is being added to the standard in C++26 called erroneous behavior. So that dereferencing an int at the beginning without initializing it, this would be an example of erroneous behavior. So this is something that's incorrect, but instead of this like rule with undefined behavior where the compiler could assume nothing ever happens, it's recommended you diagnose it. The program is allowed to just stop running if it does this. And with the case of that erroneous behavior of reading the uninitialized variable, now they have to actually return some like kind of standard result like 0 or some other sentinel value instead of just garbage, because kind of the point of making this erroneous versus undefined, instead of this, anything that happens, is kind of plugs a security leak about kind of reading memory you're not supposed to read. But the main topic of today is going to be undefined behavior. And if you want to go beyond some of the examples I'm showing about, but really get into a lot of other examples of undefined behavior, I recommend this Back to Basics talk, undefined behavior, that I have linked here. And also there's these two great articles, one by Chris Latner and one by John Ragar, about undefined behavior, that reading these articles is really what changed my thinking around as long as like I test it and check the assembly, it's okay. These articles were the ones that kind of made me change my mind that this is something that actually, we really need to avoid in our work. And from these articles, there's this concept from John Ragar of the behaviors of functions having one of three types. Type 1 functions are functions where the behavior is defined for all inputs. Type 2 functions, some are defined, some are not. So you might invoke UB if you violate some precondition. Or type 3, the behavior is undefined for all inputs. No matter what, if you call this function, you're invoking undefined behavior. So let's look at some examples. This is a type 1 function. We'll call it safe divide. And it takes two numbers, A and B. And essentially, it's going to make sure that we're not going to invoke any undefined behavior in this function, because dividing by 0 is undefined behavior, and we also don't want to do any signed integer overflow. So we have this if at the beginning that makes sure we're following the rules of signed integer division, and if we're not, we're going to just call this report integer math error and return 0 as a kind of a garbage value. And then if we're not in that dangerous, like division will cause undefined behavior example, we'll just do the division. So you see, this is safe because we'll report an error and return 0 if the division would be undefined. And then if it's defined, we just do the division. A variation of this would be a check division function that doesn't actually do any of that runtime protections, but just has assertions that B is in 0 and an assertion that you won't overflow. So in a debug build, you'll hit some assert if you're going to invoke, if you violated these preconditions. And hopefully with contracts in the future, we can do this with nice preconditions on the function signatures. But once you hit those asserts and continue on, if B is 0, this function is going to return undefined behavior, is going to be invoking undefined behavior. But if A is 10 and B is 2, this function is defined, and so this always works. And then we have a type 3 function, as our first example was, where this is until C++26, this is going to be undefined no matter what the You always call this function, it's going to be undefined. Now, it's a bit of a silly example. So here's another example that might show up in real code of something that would be a undefined behavior in all instances, which is we want a function that's going to take a float and give you back an unsigned integer that has the same bytes in it of the float. And there's various tricks that people use to do this. Union type punning. Another one is type punning with the reinterpret cast, where what this function does is going to take the address of x as a pointer, cast that from being a float pointer to an unsigned integer pointer, and then dereference the value of that to return. And this is undefined behavior because you're not allowed to access an object through a pointer of a different type. And the correct solution would be to use memcopy or bitcast for these kind of maneuvers. But this is actually one of the things that shows up a lot in debates around, like, should you invoke undefined behavior? Because I've seen this code written point out that you should use memcast, and the comment is, oh, well, but the tests pass. And actually, because the behavior is incorrect, passing test doesn't mean that anything works, because the test itself really is invalid. A test that invokes undefined behavior has the same meaning if it passes or doesn't pass, because you don't really understand, has no kind of deterministic meaning of what that behavior is. So let's look at a couple of other quick examples of what undefined behavior can cause kind of funny things to happen with the optimizer. So imagine this function situation where we have this array of 4 integers called table, and a function exists in table. We pass in an integer, and we're just going to loop through the table and check where if this integer is in the table. And you'll see there's a bug in this program, because what we have here is normally we would actually want to say write this loop as, well, I is less than size, because if we have less than or equal to size, in this case, the last iteration of the loop, I would be equal to 4. And then in the if, when we dereference the 4th element of table, or the index 4, which is the 5th element of table, that's past the end, and that's undefined behavior reading past the end of the table. And so the optimizer is allowed to make an interesting assumption. Since if I equals size, it would be undefined behavior to look for I in table, because 4 is past the end of the indices of table. That means that it's going to be impossible for us ever to get into a situation where I equals 4. So that means that for I equals 0, 1, 2, or 3, one of those 4 cases, we must find it in the table, or else we'll invoke undefined behavior. And because of that, that means that we know that this is, the optimizer can essentially say, oh, this is always true, because we know it must be in the table, or else we'll get read past the end of the array, which is undefined behavior. And so that's kind of a interesting thing. Another kind of example that shows up a lot is, and kind of tricky things happen, is null checks. So imagine you had this function that is giving you a value or an answer, and the main purpose of the function, in order to print the moment, is to see, okay, is P evaluate to true? If so, dereference P and return the value. If not, return 42. But at some point, someone came along and wrote some logging here, and they dereferenced P before the if below for this print statement. And that means if P is null, that would be undefined behavior. So again, the compiler is allowed to assume in this case that, oh, well, P can't be null because we're printing it. Therefore, we can get rid of the if and just return the value of P in all cases. And there's this great example from Raymond Chen's blog, Old New Thing, about undefined behavior resulting in time travel. And this is the kind of stuff which actually shows you, like, well, no, a malicious compiler is not going to, compilers won't be mean and erase your hard drive on purpose for invoking undefined behavior, but you could easily end up with accidental file deletion. And so that's a pretty interesting example I would check out. I don't think we have time. We don't have time to look into it today at the moment, but I recommend looking at that example. Excuse me, I'm sorry, just fast forward. Okay, I just thought I had a title slide in between these, but I guess not. So, want to also show you some undefined behavior that we found in like our own code base. And this is kind of the story of the Intel assumptions and things that work on Intel is we have um, this, we used to have some code in our code base, and this is predates the C++ memory model for dealing with atomic values and synchronization and multi-threading. So you kind of had to follow the rules of the platform. And so we had this type we called unsigned uint that was a volatile unsigned, and special functions that had different implementations on Mac OS and Windows for reading and writing that value. And so in Windows, there's a reason why this is the volatile. Like these are basically the instructions. If you want to do atomic write, you use this interlock exchange function. And then it says that the documentation say that 32-bit values are guaranteed to be atomic, and so return this. And then the Mac OS implementation did no special stuff. There was just a bunch of comments explaining stuff. Might have been from the early Apple Intel years. I think it actually from the commit date might have been from the PowerPC era, but saying that, oh, on some forums it says this is atomic and just do this. But we know that with kind of modern C++ standards, this could essentially be a race condition and undefined behavior. So how did this ever work, this stuff, without causing other issues? And I think you'll see with some of the other real world examples of bugs we've encountered, I would say don't worry about it. It's really, I think, not worth trying to understand the effects of undefined behavior in some cases, because some of them can be truly mind-boggling what weird stuff the compiler does when it assumes, oh, this will never happen, so I'm going to do something else. If you want to get this is a really big topic. And so you're not going to get into we don't have time to get into all of this today about what was wrong with those atomic read and write functions I found in our code base. But I recommend you check out this talk from Herb Sutter, Atomic Weapons, C++ memory model and hardware, that really gets into all of that. And interesting thing is, like, while most of our code was Intel, we did have at the time some iOS software and some hardware making that was ARM based, and so we did have some ARM machines that those works on Intel assumptions I showed you before wouldn't work on, but those were in different parts of our code base. Now, if you have a legacy code base that's been around for 10 or 20 years, addressing UB in legacy code can feel hopeless. And if you feel this way, I understand. It might have felt that way a little bit on our end as well. This is a slide that I probably made about 5 years ago, so the numbers might be bigger, but just got to give you a sense. If you looked across all of the Isotope plugins and applications we made, it was about 15 million lines of C++, C, and Objective-C that would show up on our code base. That doesn't mean it was all linked in every product, but this is kind of the stuff we had around in our catalog. So about 1.3 million lines of internal library code that's shared between products, DSP libraries, UI libraries, etc. About 2/3 of a million lines of product code. This is, I'm quite sure, a much bigger number. 5 years later, it might be over a million lines. I'm not sure. And then 13 million lines of open source code that, yeah, we hope they wrote correctly and is working correctly. So like I said, UB in legacy code can feel hopeless. And some of the kind of things I've heard is like, oh, there's too much to fix, so it's not worth it, or we don't have time, or we've been doing it for years. What's the problem? Why fix it? Or it works. The tests pass. The code gen looks okay. Why fix it? Oh, UB, and this is when I was heard after feedback of giving me the first time I gave this talk, that it's an intellectual topic for language nerds. Like everyday programmers don't need to care about this. And it's scrolling down. Yes, yes, I was actually in the other session, but thank you for mentioning Ofik's talk about the memory model as well. Whoever mentioned that in the chat is also worth checking out if you didn't see that today. So with that kind of sense of hopelessness in the air, what did we do to try to improve the situation? Well, we already had the first two bullets done. Is we enabled all warnings available minus maybe implicit conversions because that was too much in our code base. And we turned on all warnings as errors. This is something, if you're not already doing it in your project, I highly recommend this, at least for new code, if you can't turn all the warnings on for old code. And we were dreaming of running static analysis in CI. And at some point, we started using clang tidy on new code. And then we were aware of the Clang runtime sanitizers, asan, ubsan, tsan. We didn't feel like it was trivial to get running, and so we weren't really making use of those at first. But at the end of our story, you'll see that we are. And so when I mentioned things like asan and ubsan, when we were preparing for this talk, like I said, the first version of this talk might have been like, I forget if it was like 4 years ago or something, or 5 years ago when I gave a version of this. But we found in our Jira a ticket, research address sanitizer. And when we were preparing the talk, we realized, oh, well, we can actually close this. And it was open for 2,479 days. And I wonder what our code base quality would have been like if that research happened sooner, but it was been a really great, big deal when we actually turned this on. And so now I'm going to share some stories of fighting undefined behavior in real world code in our code base. I call them peace stories because an homage to my colleague Russell that helped me prepare an earlier version of this talk. At some point when we were crunching for a release, we decided to put all the developers into a war room, and he decided pointed out that's kind of violent. We should go to a peace room instead. So these are my peace stories, not war stories about fighting undefined behavior. So the first one is actually still the most exciting for me because it really shows trying to understand what the result of some undefined behavior will be is almost impossible to think about. So it's the attack of the Xcode update where strange stuff happening when one of our UX designers had installed Xcode via the App Store, which meant he got an automatic Xcode update, and that compiler change caused something weird to happen. So this is RX, our post-production audio repair software. And if you'll take note at the tab in the upper left of the screen, I guess my highlight is not working with the Zoom share, but and those have these trapezoid tabs that give you the file name of the track you're working on. But after this update, you'll see two strange things happen. That tab is now a long triangle, and any of these ellipses you'll see in this panel have become circles for those radio buttons became long ellipses. And we were like, that was actually kind of like really strange. Like when we said, yeah, I have to zoom in so you can see this. Yeah, it might be hard in the picture, but we have, those triangles instead of a trapezoid there and these long radio buttons. And our initial thought was, oh, maybe there's a compiler bug. And so we wanted to help file a bug report because this version of Xcode just came out. So we asked for help on IRC. We got a recommendation of this program called cReduce that essentially helps you try to like replicate an issue like this by essentially bisecting your code and deleting more and more code till it finds the code that is causing the problem. And when we ran it, all the code disappeared. And so that made us think, oh, well, that's strange. Maybe it's some undefined behavior on our part then, and not a compiler bug. And so this fourth stage we call UB the compiler. We had a guess that this was like we obviously in our draw ellipse and our draw quad functions. And the way we investigated it is we built it with two compilers and compared the assembly until we found the instruction. And this was actually by stepping through until we found the instruction that caused that was different between the two compilers, and then found where in the code the issue was. And so the moral of the story is, if you see something weird in a compiler update, you probably didn't find a compiler bug. It's probably your own undefined behavior that's the issue. Not always true. We did find one once, but all other examples, they were actually our issues, not a compiler bug. So the actual undefined behavior here was in this, like we see this draw circle outline. We see there's a few steps to actually drawing a circle in our code. We first create, this is using a drawing library called AGG. The code's a little bit simplified for slides. But first, we make an ellipse where we have an x and y and our radius. In this case, we're drawing circles, so the radius is reused. We make a stroke object from that ellipse, and then we apply a transform to that ellipse to actually position it at the right place on screen by applying that get transform to our stroke and creating this transform object. And then we add that transform as a path we can add to the rasterizer for drawing. And so this get transform, this is the source of what the undefined behavior was. So we'll see if you look at simplified implementation of transform, it has some pretty not best practices code here. You'll see two issues. One, the stroke object that's going to be passed as the first parameter is taken by reference, and then they take a pointer to that. And that's kind of okay. But then the get transform, they take a const reference. So this can bind to a temporary, and then they take the address of that and store a const pointer. There's some bad practice in general about using const objects in your classes, but the main issue here is that this get transform returns a temporary that can bind to the tr parameter of this constructor, and they take that reference. And then you see we continue to use that transform after the temporary has been deallocated. So the fix was pretty simple. We actually just get the transform, put it on the stack. It's no longer a temporary, and the undefined behavior is fixed. Now, the really crazy thing is what was actually happening that made our ellipses like this or our trapezoids like this. Well, turns out what happened is that when this undefined behavior happened of the get transform, at some point in the add path function, instead of passing x and y coordinates around, it just started passing x and x instead, because I don't know, this code is invalid because of invoking this undefined behavior here. So they can keep passing along any value, like anything was, like I said earlier, if you evoke an undefined behavior, anything is possible. And so the compiler said, oh, this is impossible. So like the code gen doesn't matter, I guess. And I pass X and X. Interestingly, I tried to, these slides I had to redo by just hacking the code to make this bug, because later versions of Clang don't cause that same strange drawing glitch with this undefined behavior, which is interesting. So there was some optimizer paths that maybe they either improved or something, but or changed, that no longer did that. So fast forward time, we've been running Clang format and Clang tidy for our static analysis, as I said, and we're not using the runtime sanitizers yet. And what happens, and we ran into a situation where your code breaks and you didn't change anything. So we were about to release a version of Ozone, our mastering software, and days before the release, there was a Windows update that came out, and then the software started crashing. The plugin started crashing on instantiation or launch 100% of the time on the latest Windows update. And so we've clearly woken some sleeping dragon before this major release. And there's a nice quote from Anthony Williams, a keynote he gave at Meeting C++ last year, that undefined behavior is often the consequence of unexpected events. And this is an example of that. And so how did we resolve this crash? We used the feature of Microsoft Visual Studio to run static analysis on one of our solutions. And it pointed out to us we had this struct for saving snapshot data, and I'll show you how that's used in a moment. But essentially, you'll notice that one of the fields doesn't have a default initializer, and all the other ones do. The way this is used is we have this feature in our mastering software called the match EQ that essentially allows you to take some audio recording, capture its spectral curve, and then apply that to your source audio. So you see in the bottom of the screen, this orange and blue curves. That's what that struct is showing this data. And the snapshot color is that orange or blue. this wasn't like, oh, us being bad programmers that caused this issue. But when this code was originally written many, many years before this version 9 update we were working on, uh, snapshot color was something chosen by the user every single time they chose a snapshot. So this was always filled in with a value. It was no point default initializing it because it was always you create snapshot data with the color provided by the user. In our new design, we're always using the same colors, but we apply those afterwards. But we also changed the way we serialize this data. We used to save it to files on disk, but now we were actually saving it with the save file in the host program we were running in their data section. And part of that save process involved some compression. And it was crashing in a situation where that second blue curve wasn't there, and that meant the color was not filled in yet. And so in that case, snapshot color was uninitialized if you were saving something in this state and trying to reload it again. And the reason for that is a little bit of some complex code is imagine we have some compress function that takes a pointer to bytes and a size and compresses it with zip compression. Our save state function was doing something that was not the most efficient and was also the source of the bug that we had here. Is it would, if you notice, it has first it computes a size, and it does it by taking the data we want to save, in this case, snapshot data. In the real world, there's actually a huge amount of data we're saving here, but we have our snapshot data, we compress it, and then we use that to get a size of like, okay, if we compress this, what size will it be? Then, for legacy reasons, that getting some APIs to dance together, the code is written to then compress the data again, and then copy that data into some vector that's the size that was pre-computed by the first compression. But what happens is when this was uninitialized, you'll see that an indeterminate value ends up getting read, and the size that was calculated from the first compression was smaller than the actual size needed by the second compression, and we get a buffer overflow in the copy. That for some reason, on previous to that Windows update, always worked out the other way, where the first compression was bigger, and therefore we reserved more than we needed when we actually did the copy. And the resolution was to short term was to just default initialize that value, so we always had a good value. And then, and then we would then also later improve that serialization code to not do that copy. And so another example of the code breaking when you didn't change it is non-deterministic test failures. So we had a situation where we have a set of DSP regression tests where we see, like, with code changes and compiler changes, does our DSP sound the same? It's not a byte for byte for compare, but like to human ears, would you be able to hear the difference between A and B is kind of what we're evaluating. And some of these tests were failing non-deterministically. When you run to that, please don't have your solution be just run it again until it passes. And this is where we first started getting into using the address sanitizer and undefined behavior sanitizer in Clang. So I went into Xcode, did this manually because we don't have it, part of our build process. And so when I turned this on, I actually was able to discover unaligned access that was going on, and this was triggered by ASAN. So to quickly show you how this unaligned access issue came up, we have a custom memory pool class that allows us to have a pool memory that we reuse for scratch data during DSP processing, because when you allocate during DSP processing, that's not real-time safe, so we try to avoid that. And we had some code that looked like this. So we would create a buffer from our memory pool of size, and in, like, let's say we're processing a buffer of size 512, and that will, let's say it creates addresses of those hypothetical range. We call analyze on this hypothetical buffer, and then we create another buffer, this time of 512 doubles. it's of that range, and everything is cool. Those are all properly aligned for those types. But now what happens, let's say we were doing some kind of analysis, like a short-term Fourier analysis, and we're doing it in the real domain. You don't need to worry about what that means, but it means you end up in situations where your analysis buffer, instead of being n the same size as your actual buffer, it would be n over 2 plus 1 in this case. And so if we do again, creating instead of 512, we're creating 257 floats for our analysis buffer. You'll see that that then means the next range taken, the next time we create a buffer of doubles starts at, instead of CEBF40, which is aligned to the size of a double, we're off by 4 bytes. And so now this is no longer aligned. And then when we call, oh, sorry, I was going backwards, call this calculation, we're going to be operating an unaligned memory. And I don't know really what the problem with that is. I've heard supposedly that like Intel can deal with unaligned memory, but the C++ standard says that's not possible. And again, how did this ever work? What went wrong? I'm not sure, but it doesn't really matter. As soon as we use UBSAN, ASAN to investigate this, it showed me exactly what part of the code base was causing this unaligned read. We made sure our memory pool buffers always return things in the right alignment, and all of a sudden, our test suite started performing deterministically. So again, like, what went wrong? Was it that, like, as I said, Intel says you can do this? C++ says you can't, so maybe it was something just about the C++ compiler itself doing something strange. We were passing this off to the Accelerate framework on Mac, where we saw these indeterminate test failures, and IPP on Windows. Was it something about the Accelerate framework was requiring alignment that we weren't providing it? As I said, I don't think it's really worth trying to understand what is going on with the UB. Just use the tools, identify it, and fix it. So to wrap up, how did we actually start making cultural and tooling changes to remove UB from our code base? First off is fear mongering. Fear running non-deterministic build failures. Don't allow people to just rerun until it passes. Also, reprioritize bugs if you can. If you fear there's some UB lurking in your code base. Another one is teaching teaching an affection. I'm sorry, that must have been some autocorrect typo I've never noticed on this slide. It should be teaching in education, and I don't know what I was supposed to say there, but evangelism. I don't know. Somehow I should say teaching and evangelism, but the idea is to teach everyone about UB, and we even made a rule not to write UB. So as I said, so to recap, fear of red builds. If you have a non-deterministic red build, you should definitely be running ASAN or UBSAN or thread sanitizer on your code base to try to identify what could be going on to cause those failures. Also, as I said, an example of fearing bugs in your code base. This is a snapshot of some parameters that go along with some of our in-product behavioral analytics. So we have like operating system, physical memory, plugin host, product name. And this primary classifier is supposed to tell you what a machine learning model detected is the genre of music that you're currently mastering when we're offering suggested settings. And you see 8 question mark or Unicode unknown. That's not one of the genres. It's things like bass, heavy, classical, country. So something's wrong there. The product manager prioritized this as a low because he was like, oh, well, I don't care. We're not really using this data right now. Who cares? But when I saw this, I was like, well, we're clearly reading garbage memory right here. And so I imagine 2 things were happening. We either get garbage results in our analytics, or someone crashed reading garbage memory. And with that fear of the crash, we looked into it, and it was a pretty easy fix that we fixed that bug. And then talking about education, at some point we were talking about UB and Slack on some issue, and one of my colleagues mentioned to me, one of the QA engineers, what's an UB? And so now we affectionately call UB UBs sometimes at work. And the point was to teach the QA engineers as well, when they see mysterious stuff happen, to kind of alert us of this risk of undefined behavior, because There's some other, strange things QA see sometimes that they're not sure to file or not when they, sometimes happens, sometimes doesn't. And then in addition to just talking to our QA engineers about it, I actually gave an internal tech talk about specifically that one bug that happened in our mastering software that was the kind of launch day crash. So it's not just QA engineers and our software engineers to understand undefined behavior, but try to really educate the rest of our friends in marketing and product design and everyone that we're working with. The kind of scary risks and how challenging it is working with C++, so that like when we're having the last minute fires to put out, they understand, what kind of, to some extent, what kind of challenges we're up against. And we made a rule to not invoke undefined behavior. So we have our own internal fork of the core guidelines. And sometimes it came up in PRs and people said, I invoked undefined behavior. And then people say, oh yeah, as I said, oh, the test passed. It works. The code gen's okay. I've done this before. This kind of debate we didn't want to have anymore. And if we already have UB, we don't want to make it worse. We want to reduce cross-platform breaks. And we want more devs watching out for UB in code review. So we made a guideline, do not invoke undefined behavior. And those debates and code reviews stopped. And, no more reinterpret casts or union type putting instead of mem copy. And the first time I gave a version of this talk, someone suggested, why isn't this part of the upstream core guidelines? And I thought, oh, it's a good idea. So earlier this year, I did open a PR. I did get distracted and haven't actually followed up on finishing incorporating these guidelines. Maybe this will be my afternoon project when the talks will be done. But if you want to join the discussion, that QR code will take you to a link. And then we also made tooling changes to start addressing undefined behavior in our code base. An interesting one was sometimes we discover functions that would cause undefined behavior. So we put deprecation warnings on those and then have a system for making deprecation warnings errors on new code. We also are running clang tidy on all new code and allowing some clang tidy refactories to work. And then slowly rolling out CI builds that are running address sanitizer and undefined behavior sanitizer and manual use of thread sanitizer, because most of our test coverage until very recently that we were using sanitizers was single threaded unit tests. And so we were manually running thread sanitizer against products. So just to give you an example of the deprecation warnings, in our signal processing code, we have a function like this for registering parameters of different types, basically like what knobs exist that you can turn. And it turned out that deep in the infrastructure that would call using a raw pointer there, even though we thought we were using this lock-free queue stuff correctly, was actually still a race condition. And so we needed a reference to an atomic instead. And so we deprecated the old version. And we have a system that means that it will fail a build if you ever use the old version in new code. And we do this with as part of our clang tidy static analysis that we're running clang tidy diff, which allows us to only check clang tidy on any change lines in our PRs. And in the clang tidy flags, we turn deprecation warnings into errors so that we will not allow people to use functionality that we know is deprecated and has UB. And some refactorings like conversion between types and stuff, it also has available to us. So like, another example of how we're using clang tidy and making custom checks is we have our own version of a optional type called checked value, or for slideware, we're calling it checked. And it has, operations like you might expect. But the big thing here is you'll notice the constructor always constructs it with a value. So when we call this cast function, it's always going the operator T. It's basically a optional that only works on default constructible things. And even if it's supposed to be invalid, you'll just get the default value if you call this operator T, which can lead to subtle bugs if that zero has meaning and isn't actually, and you wanted like, oh, no value. So we prefer people call cast instead of implicitly converting that. And so we had a check for this. So instead of having the running count, just implicitly converting like this, we want everyone to have a cast. And this is what the Clang Tidy Matcher looks like. There's other great talks on how to do this. This is a lot of code we don't have time to get into. It's not super easy, but there's some good talks out there on YouTube from past conferences about writing Clang Tidy checks. And then we also started rolling out ASAN and UBSAN for runtime checks. And our recommendation is to build and run for all of your project standard unit tests and make a plan for rolling it out. You don't have to fix everything at once, but roll it out library by library, moving up your code base and up the testing pyramid. And as you're going, some tests will fail, and you eventually start removing more and more UB from your code base. And once you have this running in CI, you're not going to be allowing that UB to come back. Um, and And so, again, some of the things that get flagged are things like this, reinterpret cast might show up in this function, and you have to change that to memcopy like we were discussing earlier. Something to keep in mind is that on Mac OS, when you're using this, you have to set this environment variable DYLD in certain libraries in some cases if you're testing like a plugin and not an application. If you try to start without setting these environment variables, you'll get an error and it will tell you what environment variables to set. One thing to watch out for is setting this with certain builds of Python on Mac OS, on modern OS versions, and their security settings has some issues, but I believe we found using Python built by PyEnv does seem to allow to use this environment variable. And as I said, we want to move up the testing pyramid. So, from unit test to integration tests to end-to-end tests. And we started moving up this with UBSAN and RSAN. So for us, we have unit tests. We have DSP regression tests, which I mentioned earlier, that allow us to compare like before and after changes on did the sound change between two different algorithms. And then we have end-to-end tests of our entire plugins. And now, actually, very recently, we have now ASAN and UBSAN running up the entire test pyramid for us. It was originally unit tests, but all levels of regression testing, integration testing, we're now using that. And because the end-to-end integration tests actually involve multi-threading, we're looking into also enabling thread sanitizer and some builds there now that we've completed UBSAN, ASAN on the pyramid. And we're also looking into, there's real-time sanitizer now available and other sanitizers. And the big part of this push and moving to try to fix a lot of our UB in our code base was Apple's announcement of switching to ARM, and all of our, it works on Intel assumptions went away. So this is when we ran thread sanitizer by hand. Since our unit tests weren't single threaded, we fixed a lot of issues to try to avoid our manual QA chasing ghosts. We found many threading bugs in our implementation that kind of worked on Intel, but you have to watch out for false positives, like atomic thread fence not being supported. So those GitHub issues from reader writer queue will kind of show you how you can work around false positive with thread sanitizers. But thread sanitizer meant we fixed all of our threading bugs that we could find and had a happy time on Apple Silicon, and also actually fixed a mysterious bug we never found before. So if you watch in this last screen, the QA is moving this slider around in this animation, and on the left side of the screen, it is recording the positions they moved. But you'll notice it did not make these smooth values that was following their mouse. It was jumping up and down and making this very jagged line. And we had no idea like why this sometimes happened. But fixing all this undefined behavior in our threading related to parameters, even if it supposedly works on Intel, that bug is gone. And we don't know what was causing it, but systematically removing UB, both with our effort for Apple Silicon to run thread sanitizer by hand and our manual work to roll out the other sanitizers across our code base is what found this. And a recent surprise that was caught by Clang Tidy that I thought was interesting is using sort. We were flagged by, I don't remember the exact warning, but that we weren't stable in our sorting. And the issue was we were using less than or equal to here when we should have used less than. It failed Clang Tidy, so it failed my build. So I fixed it. But I heard from another colleague in another company, and I won't talk about other companies' bugs, actually had an issue of this like not allowed move in standard sort that was caught by Clang Tidy actually causing a real world bug that they had to fix. So since we're closing up, I do have, if anyone's curious, I have one extra weird story. You're not supposed to const cast things, cast away const from certain things. And we did that once and we changed the meaning of silence in one of our host applications. So if anyone's curious, I can, tell that funny story during the Q&A. And again, thank you very much. Here's my contact information if you want to reach out, have any questions about tips about running sanitizers on macOS and with Python, because we've done a lot of work on this stuff. Hopefully, want to publish some blog posts about that someday. But in the meantime, feel free to reach out to me with other questions, and I'll see you over in GatherTown.